So chemical kinetics talks about the rate of a reaction, how fast a reaction occurs. So we can look at two examples here. The top series of panels is a reaction with a fast rate. So here we've got these blue oblongs reacting with these red spheres, and they're making these green ovals. And here we see time progressing, and we see that by the time we get over here, maybe that's like 45 seconds, all of the reactants have combined and all we've got left is products. Here we have a reaction with a slow rate. This happens very slowly. We've got this yellowish green and the blue making a pink oval. And so here we're starting with our reactants, and as time goes on, we start to make the pink ovals, but in that same period of time, only a few of those ovals have been created. There's only a small amount of product. Okay? Any questions? So this chapter starts kind of slow, but it's going to pick up speed. Okay? So it's super, super important for me not to lose you. Okay? Because if I lose you today, it's going to be rough. It's going to be rough. Okay? Oh, stupid. So how do we define the rate of a reaction? We use rates in everyday life. We talk about how fast were you driving, right? The speed, that's a rate. It's the distance traveled, usually measured in miles, divided by a given period of time, typically an hour. And so we often refer to the speed of a car in miles per hour. That is the rate of travel. And so we could write that as a math equation and say that the speed is equal to the change in distance divided by the change in time. And the Greek delta here, that triangle, stands for change in. So delta x means the change in the position on the x-axis, and delta t would be the change in time. So in order to find out how fast a car is going, do we need to drive it for a whole hour and measure how many miles? No. You could drive it for a minute, right? See how far it goes in 1 minute, convert minutes into hours, do a little division, and you've got your speed. So for chemical reactions, the rate is measured as a change in the amount of reactant or a change in the amount of product divided by the change in time. So let's look at an example reaction. So here we have hydrogen molecules reacting with iodine molecules to form hydrogen iodide molecules. If we start with reactants, as the reactants react, they go away, right? At the end of the reaction, if it goes to completion, there would be no hydrogen left, there'd be no iodine left. And so the change in the concentration for these reactants is negative because they started at a high value and it decreased over time. For the rate, we always express the rates as positive, and that's just a convention. So we define the rate as the change in concentration over the change in time. If we're looking at a reactant, we have to put a negative sign in front of that. So this is the change in the hydrogen concentration divided by the change in time. That would be the hydrogen concentration at time 2 minus the hydrogen concentration at time 1 divided by time 2 minus time 1. And we can do a similar thing for the other reactant, the iodine. We can define the rate of the reaction as negative change of iodine concentration divided by change in time. These are two different descriptions or definitions of the same process, and so those rates will be equal. Any questions?
The express rate is always a positive, and then there's one that's always a negative?
So we always report the rate as positive.
Right.
Just like when you're driving in a car, you don't say, well, I went minus 70 miles an hour, right? You always give it as a positive number. Now, what direction did you go in? That wasn't specified. So here we always give it as a positive number. And since the change in the hydrogen concentration is negative, in order to make the rate positive, we have to stick a negative in the front. So that's why it's negative delta H2 over dt, delta T. Anybody else? So if we look at the product here is the HI. The concentration of the product, is that going up or down as the reaction occurs? It's going up, right? We're making more product, sorry. We started with none, probably, and at the end we've got some. So the change in that concentration is positive. So we can define the rate in terms of the change in the product, and then we don't have to throw a negative sign in front of it. Really, with the negative sign here, if you just remember that a rate is positive and do the math and then make it positive. I'm not sure why they don't just say absolute value, but they don't. There's a coefficient in front of the HI. For each reaction here, 1 molecule of H2 and 1 molecule of I2, we make 2 molecules of HI. So the HI molecules are formed twice as fast as the hydrogen and iodine molecules are destroyed. So we have to take that into account. So we use this 1/2 because the rate of a reaction needs to be the same regardless of how we're defining it. So if we define it by the product, we're going to say it's 1/2, it's 1 over that coefficient, 1/2 the change in HI divided by the change in T. This change in HI, we started with 0 and we went to a larger number. This is positive, and so in this equation, just to emphasize, there's a positive sign there. We don't need the negative sign. Yes?
So if it made 3 HI, it would be 1 over 3?
Yes.
Okay.
Yep. Yeah, I kind of already said this, but that's okay. So we've got the H2 and the I reacting. So when I lose 1 molecule of I2, I gain 2 molecules of HI. So the HI is being formed twice as fast as the I2 or the H2 is decreasing. And because we need to have one single rate, then we have to account for those coefficients. So to describe the rate of this reaction in terms of the concentration of HI, it's going to be 1/2 the change in concentration of HI. It's 1 over the coefficient. And yes, that was just kind of a rewording of what I said too early on the other slide. So we could graph reactant concentrations as a factor of time. We do a lot of graphing in science because it's easier when you can see things. And by graphing, we can take a bunch of numbers and make them visual and start to see patterns. So here we have a graph where we have the concentration in capital M, that's molarity. So starting at 0 down here up to 1.8 moles per liter. And here we have time in seconds going from 0 to 120 seconds. So if we look at the change in the concentration of H2, so H2 concentration is going to decrease as time goes on because it's being used up. And here we're looking at the concentration of HI. And so this started at 0, and as the reaction proceeds, we get more and more HI. The concentration increases with time. This concentration is increasing twice as fast as this one is decreasing. And from this graph, we could figure out what the rate is, but I think that's on a later slide. Any questions?
So would it be the same, would the I2 decreasing match the H2 decreasing as well? And
So what you'd see is if you looked at the rate of HI increasing, it would be twice as high as the rate of H2 decreasing. So when we write the rate, we take into account the coefficient, so we don't have to specify what are we measuring this with respect to. Anybody else? So the average rate decreases as the reaction progresses. I feel like I'm missing something. Well, I'm maybe not supposed to talk about this till later, but I'm going to do it now because I feel like it. We can measure the rate at any given point by drawing a line that's tangent to this curve and finding the slope of that tangent line. The slope is the rise over the run. The rise is the change in concentration, and the run is the change in time. So the rate is equal to the change in concentration, so HI, divided by the change in time. And from the graph, we can measure those things directly. Now, because this is a product here with a 2 in front of it, this is being made twice as fast. To indicate the rate of the entire reaction, we have to divide by 2. It's not inconvenient at all. So here's some data in a table form. It's a bit hard to look at this and see what's going on. Here we have time going from 0 to 100 seconds. Here we have the hydrogen concentration. And these are the same concentrations as were shown on that graph. And then what we can do is we can look at the average rate for each of these time periods. So from 0 to 10 seconds, we can take the difference in the hydrogen concentration. So it's negative 0.181. And the difference in time is 10. We take that and divide by this, and we get the rate here. And what we'll see is that as time goes on, the rate gets smaller and smaller. It started at 0.0181, and it's getting smaller and smaller and smaller until we end up with 0.0030. It's a much smaller rate. So the reaction slows down as it goes along because we're getting fewer reactants. There's a lot of other reasons. Any questions? Yeah, so the instantaneous rate would be the rate at one point in time. If we wanted to look at average rates, you could, which is what we were doing on that previous slide, you could take the information at this point and this point and take those numbers and subtract, and you could get an average rate during that time period. But the rate is the slope of this line, and the slope is continuously changing. It's flattening out. The rate is becoming less. So we can do a general definition. So this is a pattern we can use for any reaction. So we're just going to use some letters here to stand in for the coefficients and for the chemical formulas. So we've got A plus B is forming C plus D, and then the lowercase letters are representing the coefficients. So A could be 2, or it might be 1. It's just whatever that number is in front of the chemical formula. So then we can define the rate of this chemical reaction in terms of any of the reactants or the products. So for reactant A, the rate is going to be negative, the change in A divided by the change in time, and then we multiply that by 1 over the coefficient. For B, it's the same, negative 1 over lowercase b, the coefficient, times the change in the concentration of B divided by the change in time. There's a negative sign there because those changes in concentration are negative. And so putting a negative sign here gives us a positive rate. If we look at the products, it's 1 over the coefficient times the change in its concentration divided by the change in time. These changes in concentration are positive, and so we don't need to mess around with the negative sign. Any questions? When we write the whole thing out like this, we see that if we know the rate of change of one of the species, we could figure out what the rate of change of any of the other species are, even if we don't know the actual rate of the reaction, but we can know the rate of each species from one, okay? At the same point in time, but at another point in time, all bets are off because, as we saw, the rate changes as the concentrations change. Okay, so let's do an example. We're given a balanced chemical equation and told that in the first 10 seconds of the reaction, the concentration of iodide ion drops from 1 molar to 0.868 molar. It says calculate the average rate of this reaction in this time interval. So the rate of the chemical reaction is the change in concentration divided by the change in time. So if we're looking at I minus, we can say the rate is equal to, this is one of the reactants, right? And so the change is going to be negative. It's going from 1 down to 0.8. And so we need a negative in here. And then we're going to have 1 over the coefficient, which is this 3 right here, 1/3, times the change in the concentration of I minus, divided by the change in time. So the change in the concentration of I minus, those brackets, by the way, just mean that we're expressing this in moles per liter. This would be the final concentration minus the initial concentration. Because almost always, delta means final minus initial. So the final concentration is 0.868 molar, and we're subtracting the initial concentration, 1.0 molar. And so if I do that on my calculator, I get negative 0.132 molar. That's the change in the concentration. The change in time is kind of just given in the first 10 seconds, right? So that's from 0 up to 10 seconds. Delta T there is 10. Delta T is 10. Oops. Seconds. So to calculate the rate, negative 1/3, negative 1.32 molarity, moles per liter, divided by 10 seconds. And so I'm getting 0.0044. And then what are the units? Molarity per second. So there's that capital M, and per second.
It'll always be in seconds.
We almost always do seconds here. The second is the base unit of time in the metric system. There are some questions that will give you the time in minutes, kind of try to trick you, but you have to convert to seconds. Good question.
Okay.
Yes?
So since we put that negative in front of the equation to make sure that it's positive,
Mhm.
our answer should always be positive.
Yep. Yeah. So your answer should always be positive for a rate, because we can't have a rate. If we said the rate was negative, that makes it sound like it's going in reverse, right? And so we're not going to do it that way. Any other questions? So there's the answer, 4.40 times 10 to the minus 3 molarity per second. That's just writing that number in scientific notation. And the second part, determine the rate of change in the concentration of hydrogen ion during this time interval. So we can talk about the rate of the reaction. We can also talk about the rate of change in concentration of each of the individual reactants and products. So what we're looking at, we want to find the change in hydrogen ion concentration divided by the change in time. That is related to the rate of the reaction, right? How is it related to the rate of the reaction?
It's 1/2 instead of 1/3.
Yeah, so it's going to be 1/2, and because it's a reactant, we have to throw a negative sign in there. That is going to be equal to the rate of the reaction, right? Now, we just found the rate of the reaction. It was 0.00440 molarity per second. What we want is we want this part. So how can we get rid of that negative 1/2?
You just
Well, there's different ways to think about it, right? You could multiply by -2. You could divide by negative 1/2. If I multiply by -2 here and times -2, what happens is the 2's cancel out and the negatives cancel out, and I'm left with the change in hydrogen ion concentration over the change in time. So delta H plus over delta T is going to be what?
negative 0.008.
-0.00880. Any questions?
Can you repeat it? I'm sorry.
Yeah, no, that's fine. Which part?
What are we calculating? So I get the molarity per second, but the bottom
Okay.
part is,
So what they're asking us for here is the rate of change in the concentration of H plus. So that's this part, delta H plus over delta T. That's the rate of change of the hydrogen ion concentration. So we can write this equation, well, I kind of messed it up, but we can write an equation for the rate is equal to, and it includes that rate of change of hydrogen ion concentration, but we want to know just the hydrogen ion concentration changing. So we took this equation rate is equal to negative 1/2 over delta t. And we're rearranging it and solving it so that we get delta H plus over delta t is going to be negative 2 times the rate.
I don't think there's anything coming up on the.
Wait for it. Maybe if I walk back this way, it'll come on. I really don't know why it does this to me. There it is. So what's a little weird about this is that we're not looking for just like X or something. We could give delta H plus over delta T a special variable name or something, but I think we've already got enough variables, right? So we just leave it delta H plus over delta T. Any other questions? The math here is not hard, right? But this is probably something that you have not seen in a previous chemistry class. And so that's what's going to happen in Chem 1B. You maybe took Chem 3A, and then when you went to Chem 1A, you're like, oh yeah, I've heard some of this before. And we just made you do harder problems, and we just went into fancier stuff, right? And so now you come into Chem 1B, and this is not just an amplification of Chem 1A. This is new stuff. Okay, and so sometimes it's just the newness is challenging. There's the answer. And then it says predict the rate of change in concentration of H2O2 and I3 minus during this time interval. And there's, oh, I think this computer's possessed. So we're looking for the change in the H2O2 concentration over time and the change in the I3 minus concentration over time. Those are the two things it's wanting us to find. Well, we know that the rate of the reaction is 0.00440 molarities per second, right? That's the rate of the reaction. If we express the rate in terms of the H2O2 concentration, the rate is going to equal negative 1 over the coefficient, right? Negative 1 over, what's the coefficient? For the H2O2 is 1 times delta H2O2 divided by delta T. So the change in the H2O2 concentration is the same as the rate, it just has a negative. Because the H2O2 is going away at a rate of 0.0044 molarity per second. Everybody okay with that?
Is it going to be the same for the I3?
Right. It will be the same. So the I3 minus and the H2O2 have coefficients of 1. And so when you do 1 over 1, it's not changing the value. And so the magnitude of this concentration change is equal to the rate of the reaction. But the change for a reactant is negative because it's going away. The change for a product is positive because it's appearing. So what's the change for the I3 minus? Well, is it disappearing or appearing? It's appearing. So this one is positive. I'm going to put a plus there just to kind of emphasize that. Because we're making this one, it's on the product side, and we're destroying the H2O2. Any questions? Yeah.
The I3 minus, is
Mhm.
that triiodine?
How would you name that? We don't teach you how to name that. Yeah.
Do we not care?
We don't care. No. So I don't know if whoever you had for your instructor in Chem 1A told you, but we lied to you in Chem 1A. A lot.
You said that you would say.
Yeah. What we did mostly was we skipped over inconvenient details. And so we taught you how to name certain groups of things, but there's a whole bunch of other stuff. And we didn't teach you that because you don't really need to know it, and it just makes things much more complicated. So off the top of my head, I'm not sure what the name of that ion is. Triiodide ion is a good stand-in, yeah. Any other questions? Yeah, so there's the answers up there. So the rates are the same, they're just opposite in sign, because one's coming and one's going. So this is a conceptual connection problem, and these problems are straight out of your textbook. This is one that we really shouldn't have to get out the calculator for. It's more conceptual. So for the reaction A plus 2B forming C under a given set of conditions, the initial rate is 0.1 molarity per second. What is the rate of change for delta B under the same conditions? So change in B divided by change in T. So if the rate of this reaction is 0.1, let's maybe do one that's a little easier first. What's the rate of change for A? Negative 0.1, right? Because the rate, I'll just write this down. For A, the rate would equal negative 1 over the coefficient, oops, I almost wrote a 2, don't know why, change in A over change in T. Right, and since it has a coefficient of 1, the rate of change for A is the same number, it's just got a negative sign. But this is asking us about B. There's a coefficient of 2. Do we multiply by 2 or divide by 2? We're going to divide by 2. So then what's the answer? It should be A, right? No. Yes, thank you. I was answering a different question. That's not helpful. So I was trying to do it, not writing it out, and we can see how well that went over. So the rate is equal to minus 1/2 the change in B over the change in T. So if this was the change in B, the rate would be half of that. That's the problem I was doing. I don't know why, because that's not the problem that's listed here, right? What we want is this part right here. The rate is 0.100. And so that's negative 1/2 times the change in B over the change in T. So we need to multiply by -2. This is a little confusing, huh? Yeah, it can be very confusing. Yes?
So, and the rate of C would just be 0.1.
Yes, the rate of change for C would be plus 0.1 molarity per second. Exactly. So it's a very good idea to be able to write it out like this. Because I just screwed it up, and I'm the teacher, right? So you get to the exam, and you have to do this problem, and you're like, uh-oh, do I multiply by 2 or divide by 2? You don't know what to do, right? If you can write out the equation, that'll tell you what to do. Any other questions?
Yeah. Do you have an advantage tutor for this class?
I do not. So how do we measure the reaction rate? We need to be able to measure the concentration of at least one of the things in there, one of the reactants or one of the products, because we can calculate the rate from that, right? So there's two ways to approach the problem. Some reactions go very quickly. So just kind of as a rough ballpark idea, if the reaction is going to finish in less than, say, an hour, what we want to do is it would be best if we can continually monitor that concentration. If it's a slow reaction that happens over a long period of time, you could have a reaction that takes 2 weeks. Do you need to monitor it continuously? No. For 2 weeks, you could probably take a sample every couple of hours and still get a good data set. So for those slow reactions, we can sample the mixture at certain time intervals and monitor the concentration that way.
Is that kind of like measuring like alcohol concentration throughout brewing and fermenting and stuff?
Yes. Yep. So one of the practical problems in chemistry is, okay, that's great, but how do you measure it, right? How do you measure the concentration? So there's a whole branch of chemistry called analytical chemistry, which is my favorite part of chemistry, that's about how do you analyze quantities of stuff, right? So one way to do it is polarimetry, measuring the change in the degree of rotation of plane polarized light. So that doesn't sound very familiar probably. So some molecules, like sugar molecules, will cause plane polarized light to rotate. So plane polarized light has all of its electric fields in the same plane. And you can measure what angle the plane is at, and if you pass it through a solution of a sugar, it will rotate the light, and you can measure that rotation. So if you have a solution where your sugar is being eaten up and it's going away, the concentration goes down and the rotation will get less and less, and so you can monitor it that way. You could look at the total pressure. This would be useful if you have a gas mixture, because the total pressure of that mixture is going to be related to the partial pressures of each gas by stoichiometry. So this example here, 2N2O is forming 2N2 and 1O2. So I'm starting with, say, 2 moles of gas, and at the end, I'm going to end up with 3 moles of gas. The pressure is going to be higher, right? And so I could measure the pressure and measure the progress of the reaction. We can also use spectroscopy, which measures the amount of light that is absorbed by one of those substances. And what we do is we use a particular wavelength of light, and we monitor the absorption of that. So here's a schematic of that. And we will be doing an experiment that uses spectroscopy. So here we have some light source, and pass that through a slit so we're not shining it all over the place. We take that light that's coming through the slit and we pass it through a prism, a monochromator, to get one wavelength of light. So we can separate the wavelengths and then just choose the one that we want. So here they're using this kind of greenish color. You pass that through the sample, and then you have a detector over here. This sample is going to absorb some of that light. And so we can measure how much is left and figure out how much was absorbed, and that's related to the concentration of that compound. In this reaction, hydrogen plus iodine to make HI, hydrogen gas is colorless, HI gas is colorless, and I2 is a violet color. It's purple, it's violet because it reflects the purple, it absorbs other wavelengths. And so that iodine is going to absorb a lot of this light. Any questions?
So if you were to shine purple through it, you wouldn't be able to measure it correctly because
You wouldn't get much absorption if you ran purple through it. And so the wavelength that you choose depends on what you're measuring. And typically what you would do is you would first look at the absorption as you change the wavelength, and then you'd find where does this absorb a lot. And I'm going to use that wavelength because that'll give me better sensitivity. For periodic sampling, say from a slow reaction, we'll take samples, those are called aliquots, samples of the mixture off at particular times, and then we'll analyze them. So we'll let the reaction go maybe for an hour, and then we'll take a little sample out and quick run our test on it to find out what the concentration is. Some common techniques here would be titration, gravimetric analysis, or gas chromatography. It has to be something that you can do fairly quickly, because in that little sample that you pull out, the reaction is going to keep going, right? And that's why you only want to use periodic sampling for something that has a slow rate of reaction. So let's look at the big idea of gas chromatography. So here we've got a carrier gas supply. So this gas supply is running through this column and coming out through this detector. We're going to take an aliquot of our sample and inject it into this stream of gas. And as this goes through the column is specially designed so it's got different substrates on it, depending on what you're analyzing and what you need to separate. And some compounds, it's a bit like the paper chromatography that you probably did in Chem 1A, where you saw that the different colors of ink moved at different speeds on the paper, right? So here, as this sample goes through the column, some substances are going to go right along with the gas and come out very quickly. Some are going to hang around on the column because their intermolecular forces attract them to the substance on the inside of the column. And so you can take a bunch of different things and separate them, and then you'll look at this detector here, and you can, what you'll typically see is a chromatogram, which is something like this. You'll have different peaks, and so this indicates one compound coming off the column, and this is another compound coming off the column. And so the concentration is going to be related to the area of that curve. We've got a gas chromatograph in the instrument room here. Any questions?
When you're taking an aliquot of something and it's time sensitive, like you
Mm-hmm.
said, does the reaction proceed faster in a smaller quantity?
Nope.
No.
No, the reaction rate should be the same regardless of the size of the mixture, because the concentrations will be the same.